Do physical things possess properties on their own, or do facts become definite only through interactions?
I mean, that is the central scientific drama of our time right there.
Yeah.
Because when we look at the theoretical rules of quantum mechanics, they're incredibly successful.
Right. The math just works.
Exactly. The mathematical formalism predicts experimental distributions of outcomes with just an extraordinary degree of accuracy.
Yeah. And we literally build technologies based on these numbers.
We do, and they work perfectly.
Right.
But, over a century after the theory was born, physicists vehemently disagree on what that mathematics actually says about reality.
Still. Yeah.
Today we're looking at Carlo Rovelli's relational quantum mechanics, or RQM, which is it's a serious interpretive proposal attempting to solve this mystery.
Okay.
But I need to establish up front, this is an interpretation. It is not an established consensus.
Right.
Nor is it the only possible explanation for the bizarre behavior of the quantum realm.
Welcome to this deep dive. Our mission today is a comprehensive overview of Rovelli's book, Helgoland, Making Sense of the Quantum Revolution. And to figure out how we got to this wild idea, we need a roadmap. So we'll start with Werner Heisenberg's 1925 breakthrough on the island of Helgoland.
Yeah, shifting physics from imagined electron paths to observable transitions.
Exactly. Then we'll explain matrix mechanics, wave mechanics, superposition measurement, and entanglement.
The heavy hitters.
The heavy hitters, right? Then we will introduce Rovelli's relational proposal and compare it with hidden variable collapse many worlds and the Copenhagen family approaches.
Nice.
Finally, we'll examine RQM's philosophical implications, its unresolved objections, and its relevance to quantum technology. All right, let's unpack this.
Let's do it.
Starting with the history. Because if we want to understand the actual meaning of quantum mechanics, we have to look at why the classical, visual models of the universe completely broke down in the first place.
Right. So in the early 1920s, the physics community was in crisis. They were relying on the Bohr model of the atom to explain atomic stability and the specific discrete spectral lines of light that atoms emit.
Okay.
That classical model treated electrons like tiny planets following hidden everyday orbits around a nucleus.
Like a little solar system.
Exactly like a little solar system.
Yeah.
But as the experiments became more precise, the math based on those visual orbits stopped working.
Oh.
The theoretical predictions were failing to match the observed spectral lines.
I see.
Physicists were essentially trying to force a classical picture onto a non-classical reality.
Right.
And they were hitting a brick wall.
So that brings us to 1925 and a young Werner Heisenberg.
Right.
He is suffering from a brutal bout of hay fever. So he retreats to Helgoland, which is this barren, windswept island in the North Sea, completely devoid of pollen.
Thankfully for him.
Right, thankfully. And out there in isolation, he has this massive conceptual leap. He realizes that the problem isn't the math, the problem is the mental picture. He decides that physicists need to stop guessing what an electron is doing when no one is looking at it, and instead they need to reorganize atomic physics strictly around observable transitions, the actual light interacting with the world.
Right. He stripped away all those visual assumptions. So Heisenberg started tracking these observable transitions using complex arrays of numbers.
Okay.
He didn't even know what mathematical structure he was building at first.
Wow, really?
Yeah. Shortly after he brought his work back, Max Born and Pascual Jordan looked at these arrays and recognized them as matrices.
Oh, okay.
So this was the birth of matrix mechanics. And the critical mechanism underlying this new math was something called non-commutativity.
Right.
In everyday math, 3 times 4 is the same as 4 times 3.
Sure, and the order doesn't matter.
Exactly. But in matrix multiplication, the order in which you multiply the quantities absolutely changes the result.
I always try to ground this non-commutativity stuff with a simple, real-world mechanism.
Please do.
Think of getting dressed in the morning. If you put on your socks and then put on your shoes, you get one highly successful, comfortable result.
Yes, you do.
If you reverse the order of operations and put on your shoes first and then try to put your socks on over them, that is a completely different, highly awkward outcome.
Extremely awkward. In the quantum realm, the order of interactions fundamentally changes the physical reality you end up measuring.
That analogy perfectly captures the mechanics of the math.
Thanks.
Heisenberg's matrix mechanics was brilliant, but it was notoriously difficult to work with and incredibly abstract.
I can imagine.
Many physicists hated it. Almost immediately, Erwin Schrödinger introduced an alternative called wave mechanics.
Right.
Mathematically, it was completely equivalent to Heisenberg's matrices, but it invited a much more comforting visual picture.
Okay.
Schrödinger used a wave function that represented evolving theoretical amplitudes over time, rather than jumping between discrete states.
But those amplitudes are tricky, right? Because they don't represent a physical wave of water or even a sound wave. No, they don't.
They are mathematical tools that eventually generate the probabilities of what we might observe in an experiment. So how exactly does that mechanism work?
Well, the translation from abstract amplitude to physical probability happens via something called the Born rule.
Okay.
You take the mathematical amplitude, square it,
Yeah.
and that gives you the probability of finding a particle in a certain place.
Right.
But the vital part of wave mechanics is that these amplitudes combine before the probabilities are calculated.
Oh, before.
Yes, if an electron has multiple potential paths, it can take the mathematical amplitudes for those paths interact with each other.
I see.
They can add together to make a highly probable outcome, or they can cancel each other out entirely.
Oh, wow.
Yeah, that combining of amplitudes before measurement is what generates the phenomenon of quantum interference. It is an underlying mechanism entirely unlike our everyday concept of uncertainty, where we just don't have enough information.
Wait, so if these mathematical amplitudes are combining before an event happens, what is the particle actually doing in reality?
That's the big question.
Right, because this leads directly to a massive public misconception regarding the word superposition.
Oh, absolutely.
When people hear that term, they casually picture an everyday object literally occupying several physical states at the exact same time.
Right.
Like the famous Schrödinger's cat thought experiment makes it sound like a cat is physically, biologically alive and dead simultaneously until we open a box.
Yeah, we have to completely separate the mathematical success of the theory from the casual mental pictures we use to talk about it.
Okay.
Superposition should absolutely not be pictured as a macroscopic object physically splitting into multiple classical conditions at once.
Right.
A particle in a superposition is not physically hovering in two distinct places like a ghost.
Thank goodness.
Right. Superposition simply means that the theoretical amplitudes describing the system are evolving according to the mathematical formalism, and they've not yet been resolved by an interaction.
Okay, so if a superposition isn't an object physically existing in multiple states, what is actually happening when a measurement finally took its place and forces a definite result?
Right.
This feels like the core problem that introduces Rovelli's relational interpretation.
It does. Rovelli's relational quantum mechanics steps in right here to solve what we call the measurement problem.
Okay.
RQM proposes something radical. It rejects the notion of an absolute observer-independent quantum state.
Oh, wow.
In this framework, a physical quantity does not possess a definite value in isolation. It only acquires a definite value relative to another specific system with which it has interacted.
I see.
The physical interaction itself is the event where facts become definite. Reality is basically just a network of these interaction events.
Okay, I need to pause on the word observer here.
Sure.
In pop science, the idea that an outcome is relative to an observer is constantly twisted to imply that a conscious human mind is required to collapse the wave function.
Oh, yeah, all the time.
Is RQM saying that the universe only exists because humans are looking at it?
No measurement does not require consciousness.
Okay.
That is a deeply flawed misconception. In relational quantum mechanics, an observer can be any physical system whatsoever.
Any physical system.
Exactly. A piece of laboratory apparatus is an observer.
Right.
A stray photon of light hitting a rock is an observer. A single air molecule is an observer. As long as a system is able to interact with another system and carry a physical record or correlation of that interaction, it counts.
Got it.
Human minds have absolutely nothing to do with the fundamental physics.
Okay, let's ground this with the three-system example from the sources, which is often called the Wigner's friend thought experiment.
Okay. Yeah.
I want to try to visualize this. Imagine a single quantum particle system A inside a sealed, completely light-proof room.
Okay.
Inside the room with the particle is detector B, a mechanical measuring device.
Got it.
Now imagine I'm standing outside the room. I am observer system C. The door is closed, and I have not interacted with anything inside.
So the experiment begins. Detector B interacts with the quantum particle. An event occurs inside the room.
Okay.
Now, relative to detector B, a definite outcome is recorded. A stable correlation has been established.
Right.
The particle was found in a specific location. However, you are standing outside. You have not interacted with the particle or the detector.
No, I'm just in the hallway.
Right.
Yeah.
Because you have not had an interaction relative to you, the compound system of the particle, and the detector can still be represented theoretically as a quantum superposition.
Wait, so you are saying there are two completely different state assignments for the exact same moment in time?
Yes.
The detector has a definite answer, but to me the whole room is still a blurry probability.
Yes, and in RQM, both descriptions are completely valid depending on the physical system you're referencing as the baseline.
Wow.
The story only concludes when you finally open the door and interact with Detector B.
Okay.
At that specific moment of interaction, your records become correlated with the detector's records.
I see.
The crucial takeaway here is that this is a purely physical perspectival claim about interaction histories. It is not a speculative claim that your personal belief creates the reality inside the room.
Right.
Facts are simply relative to the systems that interact with them.
Okay, so if physical reality is inherently relative to interacting systems, how does this compare to what other physicists believe?
Well,
Because let's be honest, physics abhors a vacuum of meaning. I know there are plenty of other interpretations trying to explain the exact same math.
oh, definitely. The alternatives approach the problem by adding different assumptions.
Okay.
Let's look at hidden variable approaches like Bohmian mechanics.
Right. Oh.
They argue that particles do have definite absolute positions at all times. They add hidden deterministic paths that we just cannot see guided by an invisible pilot wave.
Okay.
Then you have physical collapse theories.
Mm-hmm.
They propose that new, spontaneous physical mechanisms exist independent of any observer, which force a superposition to collapse into a single absolute outcome once a system reaches a certain size.
And then there is the many worlds interpretation, which goes in a completely different direction.
Yeah, the many worlds interpretation takes the mathematical formalism completely literally.
Right.
It posits that the amplitudes never collapse. Instead, every possible outcome actually happens, resulting in a constantly branching multiverse of separate realities.
It's wild.
It is wild. And finally, there are Copenhagen family approaches, which generally treat the macro world of the laboratory as fundamentally distinct from the microscopic quantum world, drawing a somewhat arbitrary line between the two.
Okay, we need to maintain strict evidence discipline here.
Always.
Bohm collapse theories, many worlds, RQM, these are all interpretive frameworks.
Exactly. They are entirely empirically equivalent.
Right.
They all perfectly predict the exact same observed laboratory outcomes. Because they use the same underlying theoretical math, no experiment currently exists that can decisively prove one over the others.
Wow.
Our preference for one interpretation largely depends on the clarity of its concepts, the philosophical assumptions it asks us to accept, and its explanatory reach.
That actually leads to another major misconception regarding Bell tests.
Oh, yes.
We see headlines all the time about quantum entanglement and Bell inequality violations.
Do you have any?
Right. People assume that because Bell tests prove that particles are correlated in weird ways, they must uniquely prove the many worlds theory or uniquely prove Bohmian mechanics.
Right. The entanglement correlations and the Bell inequality violations are observed phenomena. They're confirmed experimental facts.
All right.
What Bell tests mathematically prove is that local hidden variables cannot explain quantum mechanics.
I see.
You cannot have a universe where particles carry secret pre-programmed instructions that only affect their immediate surroundings.
Right.
But while Bell tests rule out certain local theories, they underdetermine the broader interpretations. They leave the door wide open for multiple frameworks, including relational quantum mechanics and many worlds to survive perfectly intact.
Okay, so the interpretations are tied. But I have to bring this back to reality. If RQM says that reality is just relative interactions, why does my coffee cup sitting on the desk just look like a solid coffee cup?
Good question.
Like, why doesn't our everyday macroscopic world look blurry and relative?
Well, the emergence of our stable reality is explained by a model-dependent account known as decoherence.
Decoherence, okay.
Think about your coffee cup. It is a quantum object composed of trillions of quantum particles.
Right.
But it is never isolated. It is constantly being bombarded by air molecules, photons of light, and heat radiation.
Okay.
In the relational view, every single one of those microscopic impacts is an interaction. The environment is basically measuring the coffee cup trillions of times every millisecond.
Oh, wow.
Stable macroscopic facts arise because of these incredibly dense, redundant interactions. They create massive environmental correlations that rapidly bleed away all the strange quantum interference effects.
I see.
The classical limit, our normal everyday world emerges simply because of the sheer overwhelming volume of continuous physical interactions.
Here's where it gets really interesting, because if the entire universe is built on physical interactions and correlations, how do we handle action at a distance?
Right.
How does entanglement operate under this relational view, and how does it impact the quantum technologies we are building today?
Well, entanglement occurs when two systems have interacted in the past, meaning their theoretical amplitudes remain mathematically linked.
Okay.
When you finally interact with one particle to measure it, you immediately know something about the state of the other particle, even if it is light years away.
Right.
Entanglement yields strictly observed correlations between distant systems.
We need to stop right there and correct our fourth major misconception.
The big one.
Because the moment people hear action at a distance, they think we can use entanglement to build a faster-than-light telephone.
Right. And the idea that entanglement enables controllable faster-than-light communication is entirely false.
Good to know.
Quantum mechanics preserves operational no signaling.
Yeah.
Here's the mechanism. The outcome of your measurement is fundamentally probabilistic. You cannot force your particle to become a 1 so that your friend across the galaxy instantly receives a 0.
Right. You can't control it.
Exactly. When you measure your particle, it just looked like random noise.
Oh.
You only realize the systems were correlated after you both measure your respective particles and compare notes.
Ah.
And comparing notes requires sending a message through traditional means, which is fundamentally limited by the speed of light.
Even without faster-than-light messaging, the observed quantum technologies we are engineering right now are incredible.
They really are.
We are building quantum computers, quantum cryptography systems, highly sensitive metrology sensors, and complex teleportation protocols.
Yep.
If physicists can't even agree on an interpretation, how are engineers building machines based on this science?
Because the technology relies strictly on the theoretical mathematical formalism and the observed experimental results.
Okay, that makes sense.
Quantum technologies exploit theoretical resources like qubits and entanglement incredibly effectively to process information in ways classical computers cannot. A classical bit is definitely a 1 or a 0. A qubit utilizes those uncollapsed amplitudes to hold complex probabilities, allowing the computer to perform vast calculations simultaneously before forcing an output.
Wow.
The engineers building these machines do not need physicists to settle the philosophical debate.
Yeah, they just need it to work.
Exactly. A quantum computer calculates the exact same way, regardless of whether the engineer believes the universe is branching into many worlds or if they believe reality is entirely relational.
But Carlo Rovelli clearly believes the relational interpretation has profound implications far beyond just making the math work for a computer.
Oh, absolutely.
In the sources, he draws massive philosophical connections. He traces lines from physicists and thinkers like Ernst Mach and Alexander Bogdanov all the way back to the ancient Buddhist philosopher Nagarjuna.
He goes deep.
He focuses on this grand idea that the universe is not made of intrinsic self-standing substances or solid building blocks, but is entirely an infinite web of relations.
We have to apply our evidence labels very carefully here, though.
Right.
When we stretch the physics toward consciousness meaning or ultimate ontology, we are firmly in the realm of the philosophical or speculative.
Here.
Rovelli is offering fascinating historical analogies that certainly illuminate the relational viewpoint, but exploring Buddhist philosophy does not constitute experimental confirmation of quantum mechanics.
Hold on, I have to push back here.
Okay.
If we take this philosophical leap that reality is just a web of interactions, what it's actually interacting.
Right.
It sounds like you were describing a bridge, but you were telling me there are no riverbanks on either side.
Yeah.
How can a relation exist if there are no intrinsic self-standing things to relate to one another in the first place?
It's tricky.
Does RQM actually solve the measurement problem, or does it just reframe it in a way that creates a massive logical paradox?
This raises an important question, and you have just hit on the most serious objection leveled against relational quantum mechanics.
Oh, what?
The debate centers on the status of relations versus relata. The relata are the things doing the relation.
Right, the riverbanks.
Exactly. RQM gains a lot of conceptual economy by throwing away the absolute heavy quantum state, but critics argue the cost is an underspecified ontology.
I see.
If a particle only has properties relative to a detector, and the detector only has properties relative to the scientist, it becomes an infinite regression.
Wow, yeah.
Furthermore, critics question how we guarantee intersubjective agreement.
Meaning what?
Meaning, if facts are relative to different interacting systems, how do we mathematically guarantee that cross-perspective consistency is maintained when all those observers finally get together and compare notes?
So what does this all mean?
Well,
We've covered Heisenberg's island epiphany, the differences between matrix and wave mechanics, the nuances of superposition and Wigner's sealed room. The competing interpretations and the heavy philosophical implications of a purely relational universe.
Ultimately, the key discipline for anyone exploring this field is to fiercely separate mathematical success from the mental pictures we use to explain it.
Right.
Quantum mechanics is an extraordinarily accurate, experimentally proven framework. The math works.
It absolutely does.
But an interpretation asks what entities, events, or relations actually make those mathematical predictions intelligible.
Right.
Relational quantum mechanics asks us to abandon our comforting classical picture of absolute independent properties. It suggests we view the physical world as a sparse network of interaction events.
It's beautiful in a way.
It is.
Yeah.
It is a powerful, elegant reframing of the science.
Yeah.
But as those objections highlight, the debate over the true nature of reality is far from settled.
It is a profound shift in how we might view the universe. Before we wrap up, I need to explicitly state that this deep dive is an independent COSMORA HQ book overview.
Right.
We highly encourage you to seek lawful access to the full book Helgoland through a library, bookseller, publisher, or authorized digital or audio service.
Highly recommend it.
There is so much more depth, history, and physics to explore in Rovelli's own words. We also invite thoughtful discussion from you, our listeners, on the topics we've covered today.
There's certainly plenty to discuss. The quantum revolution forces us to tear down and rethink the very foundation of what we consider real.
Is reality ultimately made of things, or of the interactions through which things become meaningful to one another?